This is one of the most important data structures in modern programming, but what you think it is and how it works might vary quite a lot depending on the kind of programming you've done in your career so far. If you're used to languages like JavaScript or Python, you're probably familiar with the properties of this data type. It can store elements of any size, any type, and it can also grow to any length, within the constraints of your computer. This is a remarkable degree of flexibility, so how does it achieve this? What actually is it, and how is it organized? Is it a list or an array, and is there any difference between those terms? That's what this video is about. Through it, I hope you'll understand better the data structure you probably use more than anything else, as well as unlock some ideas that will help us begin to explore early programming languages. Let's get started. And we'll start by looking at arrays. One way you can think about data structures is according to their abstract data type. An abstract data type is essentially what we as programmers might call the interface for a data structure, the operations you can perform, or to put it another way, the methods you can call and how they behave. Perhaps the most basic set of operations we might want of an array is to construct a sequence of elements in an order and to access them by their index. Now, every data structure has to eventually come down to bytes in memory. And we saw in previous videos that modern memory is essentially a long list of cells, each of which has an address and each of which can store 1 byte. So laying out an array like this in memory is pretty straightforward. To implement an array, we'll have to create a little program for each of the operations we want to have. In this case, this is just construct and retrieve so far. We'll implement these programs using an imaginary assembly language that looks a bit like this. If you don't know anything about assembly, just imagine that these are functions which move data around, and I'll talk you through them as we look at them. Hi there, me from the editing studio, which is really the same place as the normal studio, but I thought it would be worth me saying a bit more about this environment because you're going to see it a lot in this video. Essentially what we've got is some code on the left and then some areas in memory that we can change on the right. We've got on the right the top section which has the registers, and you can imagine those as the kind of immediate current variables that the program is using if you don't know what a register is. And then on the bottom we've got the memory which is used to store things like data structures in. As the program runs, you'll see the code get executed and change the values in the registers and the values in memory too, depending on what the command does. The registers also break down into 2 types. We've got the X registers on the right, and they're for just general purpose usage, and we've got the P registers on the left, and those are designed to point to areas in memory. To make this a bit easier to follow, once we've got a few pointers flying around, I've given each of the P registers a little tag, which is going to follow it both next to the actual register and in the memory section as the address in the register moves around. So you can see right now we have 02 in the P0 register, and so the cell 02 in the memory section is highlighted with this P0 tag, so you can see that the P0 register is pointing at that exact location. The code on the left is a made-up assembly language, which is for a made-up computer, which I've created just for this video. It's made up of a list of commands, each of which alters the registers or memory in some way. For example, this move command moves the value in the PM register to the P0 register, and in general with these commands they move from left to right according to the direction of the arrow. Some of the commands, like inc, only have 1 register and so only operate on that single register, whereas some operations like store will work in a more complex fashion. So store in particular is going to store the value, in this case hex 63, to not the register P0 because it's got these square brackets around it. What these square brackets mean is that we're going to look at the register P0, we're going to interpret its value as an address in memory, and then we're going to perform our operation on that address in memory, not on the value in the register. So in this case, the store command is going to take the value hex 63, it's going to look at the register P0, and then it's going to actually store this value into the cell 02 in memory. And the load instruction is going to work kind of the opposite way. It's going to look at the register P0, interpret its contents as an address, go to that address in memory, and then load out of that cell into the register X1. Now as these instructions execute, you will also see that some of the cells get highlighted, and this can be useful for you keeping track of what's going on. So the rule is cells that are being accessed will highlight in this lighter grey, and cells that are being changed or about to be changed are going to be highlighted in yellow. So this should help you keep track of what the instruction is using and what it's then altering. As the video moves on, you'll see things get more complex and new visualizations will show up, so don't be afraid to pause the video and go back over some bits if you really want to dig into how these individual pieces of code are working. In general, you should be able to follow what's going on purely by focusing on the memory picture, but the code's there for you, so you can pause it and pore over it in detail if you would like. Alright, that's probably enough about that. Let's get back to talking about arrays. So, if we want to construct an array, and assuming that each of our elements is 1 byte long, then we can construct by somehow reserving or allocating 5 cells of memory and then putting each element in a single cell. We also store a reference to the first cell in the array in one of our registers, and this is analogous to the array variable. Now, the process for allocating memory can vary a lot between different computers and operating systems, and it can also get fairly complicated. So for this video, we're going to work with a very basic model of it. Imagine that when a program starts up, the operating system gives us an address in memory that we can use everything after however we like. Every time we want to create a data structure, we put it at that address in memory, save the address to a register, and then increment the address in PM by however much we've used. So we're using the PM register here as a pointer to the next address in memory that we can use if we need to allocate a new data structure. Now, this isn't exactly how it works in reality, but it isn't too far off, and it's simple enough to let us focus on the data structures we're going to look at today. Now let's look at retrieving elements from an array. For retrieval, we can take the address of the first cell and add to it the index that we want to retrieve. The same logic works for storage too. Just take the address of the start of the array and add the index that you want to store to. If you've ever wondered why arrays in programming are commonly zero indexed, this is one very good reason why. It makes it trivial to calculate where elements in the array will exist in memory. If we wanted to have an array like this which was 1 indexed, well then we'd have to subtract 1 every time in the language implementation, and I guess we don't really want to do that. So 0 indexed it is, and it does kind of make more sense when you see it like this. One important way we can analyze a data structure is how long it takes to perform important operations. We could try to actually measure how long it would take to, for example, construct a new array of 5 items. But this is going to vary a lot from computer to computer, so it isn't especially useful in the abstract. We could instead count the number of operations that it takes to perform a given task. In this case, it takes us 11 operations to store an array of 5 items. This is more abstract than timing, which allows us to compare 2 implementations of the same basic algorithm, not worrying about which computer they're running on. For example, we could optimize this algorithm for performance by using scaled index addressing. Scaled index addressing, by the way, is those little sums inside the square brackets. They have a rather interesting way of being encoded in assembly, and we're not going to go into it today, but if you're interested, then there's a little bit more about it in the assembly videos on this channel, as well as if you're an OODS member, you'll be able to go in and do the Build Your Own Disassembler project, which goes into scaled index addressing in a lot more detail, and it's pretty interesting stuff. Anyway, let's get back to the topic at hand. Now, the exact same task only takes us 7 operations. But in reality, maybe this scaled index addressing is just going to do another instruction behind the scenes, and if that's the case, maybe this algorithm isn't going to be any faster than before, or maybe it might even be slower. The problem is, speed is a function of both the machine and the algorithm. So whenever we're talking about speed, we're necessarily talking about both of those things, and there's not really any way to get away from that. Now, many of you watching this will be waiting for me to invoke a special idea. But before I do, I want to impress this idea on you. What we're about to talk about is not speed. You can, as a software engineer, focus on speed, and that's great, but what we're about to talk about, it's something subtly different than speed. Now, you will have noticed that the number of operations it takes to construct an array is related to the number of elements that an array has. It's not exactly the same. We've got those 2 instructions on the start too, but we can say that the number of operations it takes to construct an array increases in direct linear proportion to the number of elements in the array. If we were to plot this algorithm on a graph, it would look like this. It hits the y-axis at 2 and increases directly in line with the size of the input, which we'll call n. Our previous version of this algorithm, which needed 1 operation at the start for setup and then 2 per item, would look like this. Now let me ask you a question. Imagine constructing an array of 100 elements. Which of these algorithms is going to be faster? I'll give you 3 different options. The one in the red is faster, the one in the blue is faster, or we can't tell. Now, if you answered G, the one in the blue is faster, you're incorrect. If you answered F, the one in the red is faster, you're also incorrect. The correct answer is We don't know. We can't know because this graph, the number of operations, doesn't tell us anything about speed. Speed depends on both the algorithm and the computer the algorithm is running on. The way the machine and the tooling works may cause both to be the same speed or one to be faster than the other, even if they're running on the same machine. So we can't know which is faster just from this information. But this graph does tell us something very useful, and that is the relationship between the speed and the input size. In both algorithms, the number of operations increases in linear proportion to the size of the input. We can see this both from the equations and from the shapes of the lines. And this relationship between the speed or the number of operations and the input size is much more independent of changes to the machine or even of tweaks to the algorithm. Let's say that we ran both algorithms on a machine that magically manages to optimize our algorithm to run in a fifth of the number of operations. Even then, every one of these algorithms is going to take roughly 10 times longer to construct an array of 500 elements than it does an array of 50 elements. Let's look at the time complexity of retrieving or storing a single item. It looks like it's just going to take one operation, no matter how big the array is or what number element we want to retrieve. Or it might take two if the processor has to do that addition for itself as well. Let's plot the one operation algorithm on our graph, and then for sake of argument, imagine that some poor programmer had to write this at 4 AM and accidentally made it 10 operations rather than 1. As we can see, regardless of the actual number of operations, the number of operations as n increases, as the length of the array or the element we want to retrieve increases, is constant. It's always going to be either 1 or 10, no matter what. This algorithm's relationship to its input size is fundamentally different to the construction algorithm whose relationship we saw earlier. For this algorithm, no matter how large the input is, the number of operations is constant, whereas for the one we saw earlier, the number of operations would increase linearly as input size increases. This relationship, which in computing we call time complexity, is very useful. We have a special notation for it that allows us to categorize algorithms according to their growth rates, and it's called big theta. Yes, that's right, it's theta. You've been lied to all these years. It's not called big O at all. Well, it kind of is called big O casually, but basically it's theta. And, well, everyone uses the term big O anyway, so we should probably use that too in order to make sense to the people we're working with, but one day we'll talk more about big O and theta and a few other things. The formal ideas behind big O are actually quite interesting and pleasing when you look at them, but not right now. For now, we'll use the ordinary everyday terms programmers use and say that the upper four red and blue functions have linear time complexity, also known as ON, meaning that the number of operations grows in linear proportion with the size of the input. And the lower green functions have constant time complexity, also known as O1, meaning that the number of operations is constant no matter how large the input is. Again, this doesn't mean that the algorithm is going to be fast or slow. People often use time complexity and big O to think about speed, and that's usually pretty useful. The reason that we can hand-wave big O as speed is because in general, for software above a certain level of complexity, as the years go by, computers get faster and inputs get larger. So algorithms with worse time complexity tend to be real-world slower, and they get even slower as time goes by, more people exist, they use the internet more, and so on. While smaller factors in the algorithm like +1 or multiply by 2 tend to become less and less relevant. But it's important for you to know, as the kind of serious, deep thinker type of software engineers who watch this channel, big O isn't about speed or slowness. It's about the rate at which algorithms get slower as the input size gets bigger. Knowing this allows you to perform some magical feats, like choosing a higher time complexity algorithm when the situation suits you. And we may cover that more later. Now let's recap the big O time complexity of our array's operations so far. And it's looking pretty efficient. It's hard to imagine anything more efficient for constructing retrieval and storage. If you want a fun thought exercise though, try to think about some ways you could implement array construction in constant time. I know that may sound ridiculous, but I think theoretically there is actually a way to do it. So put it in the comments if you come up with it. Oh, and I should say before you rack your brains on this, it's a very impractical way of making array construction constant time, so don't worry about it too much. In any case, right now our array implementation can't do very much more than store and retrieve single byte elements, and that's basically just how memory works anyway, so it's not that impressive. Let's add some features. Now, it's probably reasonably safe to say that most programmers don't want to limit the size of their numbers to a single byte. So what if we want to store numbers that are larger than that, say numbers that take 2 bytes? We only have to make one adjustment to our algorithm. Multiply the index by the size of the value. This then lets us allocate 2 bytes per element. This is again using scaled index addressing, but you can imagine it just as this mathematical expression. We're also storing these little endian, by the way, and if you don't know what that is, it's basically storing the bytes in the reverse of how we look at them as humans. And I'll put a link to my video which covers endianness in the description so you can see more about that if you're interested. Now we can build on this idea to say that as long as the element size is fixed and constant, we can store anything in an array. For example, we could store an array of 3D points, each of which is an array of 3 2-byte integers. What about other data types like strings? This is fine too. It's the same principle. So long as each string is the same length and we know that length up front, we can handle it just like those 3D points. But what if we want to store items of varying sizes? For example, the names of some people. This is where things get difficult. If our items vary in size, we can't calculate where elements are purely from the index anymore. Now we could try to have some sort of separator like a null byte. Constructing arrays would still take linear time, but accessing items would involve going through each item in the sequence with a counter. Accessing items then also takes linear time, not constant time as before, which is not so good. Probably the best we can do is to try to work out some sort of sensible limit on the length of names and use this to construct an array with items of that fixed length. If you have a particularly long name, you may have come across situations where your name was too long for some computer system, and this kind of decision making may be the reason why. Now all of this already isn't great, but we're not done with the downsides of arrays yet. What if we wanted to insert an item in the middle of an array? Now we can't just create a new memory cell in the middle, and instead we need to move every single item after the slot we want to add down by 1. This would be particularly expensive if we wanted to add an item at the start of a very long array where the elements themselves were very large. But it gets even worse. As it is, we can't even do that. By the time we wanted to add an item to our array, we might actually have used the memory straight after the array, leaving no space for us to add a new item, whether it's at the start, in the middle, or at the end. Unless of course we wanted to move every data structure our processor is using one step later and update all the references to those data structures too, which is not really practical. All of this is why with this data structure, which is the one C arrays use, you need to specify the size of the array and the size of its element data type up front, and you can't change either thereafter. And because C strings are broadly the same as C arrays, the same principle applies to strings too. You must specify its size when allocating it. Now there are some ways around these shortcomings. Let's say if you wanted an array that you could add items to later, you could allocate an array larger than you thought you'd need, and then use a variable to keep track of the last index you used. When you add an item, you can increment that index, and when you remove one, you can decrement it. This will work and you'll get the same performance so long as you don't ever need to add one more item than you pre-planned for. If you do, then your program breaks. Or if you wanted to store an array of different sizes of items, then instead of storing the array of items themselves, you could store an array of the addresses of those items and store those items elsewhere. We might call this an array of pointers. This makes things a bit more complex, but it does let you store an array of items of varied sizes. Now, if you're a Python or JavaScript developer, you will by now have worked out that the data structure you know as the square brackets one can't possibly be an array like this. You know that the structure you're familiar with lets you add and remove as many items as you like, and I bet Python has never told you array's full, plenty of memory left, but this array is full. The idea is just absurd. So these languages must be doing something different. So let's look back at this array of pointers idea. An array of pointers conceptually looks like this. We have our actual array up top here, but instead of being an array of 3 values, it's actually an array of 3 pointers to locations in memory. That's that grid we saw before, memory where the values are stored. But there's another way we could do this. What if we created one array per element we wanted to store? This array, which we'll call a record, has only 2 elements, the value itself and an address which we'll call link. This address would then point to another record, the record for the second element in the list. and this record's link field would point to the third element, forming a chain. This data structure is called a linked list. And while we're here, for reasons that will become apparent later, the link address typically comes first, so let's swap them over. Let's look at how we might implement construct, retrieve, and store for this structure. Now, construction is just a little bit more complicated than allocating an array. We're going to construct a list of 3 items, 1, 4, and 9. We'll do this by constructing a chain of 3 records. Each record is made up of just 2 elements, a pointer to the next record and the value itself. We construct the linked list in reverse, starting with the last item. We can't construct from the first record because we then need to know what the address of the second record is, and we haven't made it yet, so we start from the end. For the final record, we set the link field, the pointer to the next record, as 0 or null and just store the value. This 0 then acts as a signal that we're at the end of the list. And as a fun side note, this using pointers to address 0 as special values idea it's not exactly the same, but it's conceptually the root cause of the dereferencing a null pointer error. Address 0, which you'll notice I've conveniently avoided using throughout this video, is typically reserved and inaccessible. Not always though, but it makes me wonder, what is in that byte at address 0 in my computer's RAM? Secrets of the universe? Whether Tim Cook likes cilantro? Please drop a comment if you happen to know what's there. Anyway, we added the final element, so now we just repeatedly prepend to the list, adding the items in reverse. We use the P1 register to store the address of the last record that we added, and for each item we allocate 4 bytes, store the address of the previous record in the current record's link field, store its value after that, and then store the address of the current record in P1 ready to add a new record. We repeat that process once more, and then we handily have the address of the first record of the list in our P1 register. A little practice for you. What is the big O time complexity of this linked list construction algorithm? And how does it compare to the time complexity of constructing an array? I'll let you think on that one. To retrieve a value, we go through each record with a counter. We start that counter with the index of the element we want to retrieve, in this case index 2. Then each time we process a record we decrement that counter, and when the counter hits 0 we've found our record. I'll explain how this program works to you. First we keep track of the current item in the P1 register and the index of the record to retrieve in the X0 register, while P0 is the address of the list. We go through in a loop. First we check if the index, that's register X0, is 0, and if so, we jump to the success condition. Otherwise, we load the link address from memory into the P1 register. We then decrement the index in X0 and jump back to the top of our loop. Once we find index 0 and we're done, we have the address of our record in P1. We can then load values from it and store back to it just like we did with arrays. If you squint a bit, you'll see that both of these construction and retrieval operations are pretty neat recursive operations. In Python, they might look something like this. A little less elegant in Python than some other functional languages, but still reasonably elegant. We've talked quite a bit about recursion on this channel so far, and so you may remember that whenever we're looking at a recursive algorithm, we should be thinking, this problem is being solved with a stack. And you may also remember from the stacks video how much drama there was about getting recursion into the ALGOL programming language. If you have a very, very good memory, you may recall that while Dijkstra was at the center of all the drama, he wasn't actually the first person to propose adding recursion to the language, though the person who did propose it first wasn't quite as pushy as Dijkstra and got overruled. But more on that later. Let's look at some more perks of the linked list. For example, inserting a new item. If you want to insert a new item at the start of a linked list, it's very straightforward and you've actually seen it already, because that's all constructing a linked list is, repeatedly prepending to the list. And these records don't need to be contiguous like an array does. I've put 4 bytes in between them here, but they could easily be very far apart or in a completely different order, since the pointer is used to decide the sequence, not the memory address. And you can insert into the middle too, and here's how you do it. Firstly, you create a new record for the new element you want to store. Then you seek to the record directly before the position you want to add your new record in. And then you splice it in by adjusting the linking fields. The record before the position you want to insert into should be adjusted so that its linking field points to your new record, and your new record's linking field is going to have to link to the record after the point you want to insert into. And just for fun, since somebody on X just mentioned how they found reversing a linked list a bit bamboozling, here's a program that does just that. Basically, you just have to go through the list reversing all the links, but it's a little bit fiddly to do. Fun to watch though, I think. But I think I liked it better how it was. One of the other neat things about linked lists is that you can use them to store items of varying lengths. To achieve this, we'll store the link just like before, but our value will work differently. First, we'll have 2 bytes storing the length of the string, and then we'll store its actual contents. This linking strategy means that we don't have to worry about needing to be able to calculate the address of the item based on a fixed item length. As long as we follow the links, it all still works. And alternatively, in this case, we could use null terminators on the strings rather than lengths, although that only really works for strings, so we've used the length anyway. I also mentioned earlier that we'd talk more about why the linking field came first, and this is one very good reason why. If it came after the variable length payload, then we wouldn't really be able to access the linking field so easily. So this linked list data structure is looking very nice. Now we can not only construct, store and retrieve items of any length, but we can also add and remove items or even sequences wherever we like. There's just one issue. It sucks. Look at the time complexity for storage and retrieval. Linear. Sure, it can insert and delete elements in constant time, but storage and retrieval are 2 really critical operations, and it seems very foolish to trade them off for better insertion and deletion. And these insertions come with a big asterisk as well. Prepend is genuinely constant time, but to insert, append or delete, you have to access the right place in the list first. And this means in many real-world contexts, these operations are going to take linear time, not constant. Prepend isn't victim of this because we don't have to search the list to find the first item since we've already got it. And that isn't even all of it. When it comes to actual speed in the real world, linked lists might be scattered all over memory and therefore take the computer extra work to fetch into the fast access cache. Since arrays are stored contiguously, they don't have this problem. Both arrays and linked lists seem to have these really significant drawbacks. Linked lists are flexible to any element size and length, but have this terrible performance penalty except if you only care about prepending. Arrays have great performance characteristics, except if you need to insert a new item in the middle, but they also have this big downside where you need to provide a fixed element size and length, or at least maximum length, up front. If you're a Python or JavaScript developer, you will by now have worked out again that the data structure you know as the square brackets one can't possibly be either of these. You know that they're flexible in size, and you're probably also pretty sure that they can't have such terrible performance characteristics for access. They must be using some magical structure which is able to be both flexible in size and also fast for access. And they do. It's quite simple, really. Remember how before we created a capped array by creating an array longer than we thought we'd need and then using a register to keep track of the number of slots we'd actually used? This is a similar idea. But when we need to allocate an element the array doesn't have space for, and here I've just added some junk data in blue so you can see there's no more room to expand it, we create a whole new array at double the length, insert the new item in the right place, and then copy over all of the old items. In the real world, we'd probably then tell the operating system that we didn't need space for the old array anymore, or in some other way free up that space for potential reuse. This data structure is known as a dynamic array. As you can see from the somewhat too small font, this takes a bit more code and a fair few operations too, but it's not so bad. Let's look at a larger example where I'll show you just the code for adding new elements, and you can keep an eye on the memory and time. Most of the calls to add item run in constant time, O1. No matter how big the array gets, they take about 5 operations. But sometimes, when the array is full, they take quite a lot longer, needing to copy over the old array to the new location. This operation, resizing the array, runs in linear time, ON. But we only need to resize the array every so often. In this algorithm, we double the size of the array each time, and in this case that means that for a starting size of 2 and adding 14 items, we pay that cost 3 times. Once to allocate an array of size 4, then of size 8, and then of size 16. If we abstract away from this example a bit, let's say we create an array of 1 item and keep adding items to the end. At first, our array size will be just 1, then 2, 4, 8, 16, 32, and you get it, it's the powers of 2. Each time we hit one of those thresholds, it will cost us the length of the list so far. So to add 32 items to an empty list, it takes 63 actual storage operations, and each of those will count as just a single operation. That's an average of 1.97 operations per item. If we plot out a graph of the number of operations it takes to add n items to an empty list, we get this. As you can see, it seems to be a funny stepped sort of curve, generally bracketed by 3 and 2. And this means something very important. It means that while the occasional append operation might run in linear time, on average, it's a constant time operation. So you will often see this referred to as the amortized time complexity. Amortized means that we're averaging over a sequence of operations, not taking just one in isolation. I've just chosen the doubling behavior for simplicity. Real programming languages probably default to constructing larger arrays initially, and I think a normal resize factor is something like 3 times larger each resize. And it's worth noting that we can of course use the pointer technique from before to store lists of pointers, which themselves point to types of varied lengths. All of this gets us a very nice data structure, one that's definitely worth building into the core of the most popular programming languages. And that's what it is, at least most of the time. Here's a table of some common data structures you might find yourself using in your languages. These things can be a bit more complicated than one type equals a specific data structure, and researching them isn't super straightforward, so treat this as a general idea. There might be some inaccuracies here. For JavaScript in particular, the runtime often tries to work out whether it should store an array as a dynamic array or as a dictionary if there are keys which are very far apart, sometimes known as sparse arrays. And in general, the more systemsy your language is, the more likely you are to be given a choice of different data structures. So for Golang and Rust, you probably already know the type you're wanting to use. I've been kind of harsh on linked lists in this video, but I don't want you to think I don't like them. In fact, I like them quite a lot, and we're going to explore them a fair bit in the next few videos. There are some programming languages which use linked lists as a core part of the design. I mentioned earlier that there was someone else before Dijkstra who proposed putting recursion into the Algol programming language. That person was John McCarthy, and I imagine he was keen on recursion because he'd just designed his own programming language which made heavy use of linked lists. That language is one of the oldest programming languages in use today, and it's called Lisp, which stands for List Processor. It uses linked lists as its core data structure. In fact, even that is not putting it strongly enough. Other languages which make heavy use of linked lists are F#, OCaml, and Haskell. So why do they do that? It's an interesting question. You may get a feeling from the languages I've mentioned some of the reasons that it might be. And we're going to explore this in a bit more depth in some of the future ODES videos. For now, this, like every ODES video, comes with some exercises so that you can put this stuff into practice yourself and really get it into your own brain. For some theory exercises, I think you'll learn quite a lot from implementing these two data structures, the linked list and the dynamic array. You can use whichever language you want, but if you want to give the dynamic array a go in assembly and the linked list a go in some language which supports recursion, which is most programming languages, I think you'll get the most out of it. Still, if you don't know assembly, or if you perhaps don't know a language which supports recursion, although that would be quite unusual, then just give it a go in whatever language you feel most comfortable in. It's not a huge deal. You'll also need to make some slight changes to the approaches that I've shown you today. For example, if you're making a dynamic array, you probably don't want to store the length of that array in a register only because you're going to need those registers for other things in your program. So you probably want to store it in memory instead. So don't treat it as you have to implement it the way that I've done it in the video. There will be a few leaps you'll need to make. I've also provided some extra challenges which make things a bit more tricky. For the ones that ask you to change the time complexity, again, diverge as much as you need to from the structures that I've shown you today. I also include an extra exercise for ODES members in every video as a thank you for supporting me to do this project. And ODES membership is £10, dollars, or euros a month, depending on where you are. And for that, you get ad-free viewing of these videos, as well as extras with every video, including exercises and projects and things like that. Plus, of course, a lot of gratitude from me. This video's members only exercise provides you with a binary file, which contains a linked list, which contains a run length encoded binary file, which contains a linked list. And at the end of that, there's not a prize exactly, but there's something to find out. So it's a good drill on learning to use linked lists and binary formats. I had a lot of fun putting this one together, and so if you're an ODES member, I hope you have fun doing it too. If you'd like to sign up for a membership, then you can find the link in the description, which will take you to a place with this video and all the exercises from it and some extra resources as well as some buttons and links, which will guide you towards signing up if that's what you'd like to do. That's all for this video. The next couple will probably be exploring some smaller topics around this area, and then the next big one after that will be probably to do with Lisp or Forth. I'm not quite sure which one it's going to be yet. This video was actually sparked by me investigating Forth and wanting to do a video on it, and then learning that Forth uses a linked list to store its keywords, and then being sort of puzzled by that and eventually finding out why that is. But we'll talk more about that in future. Thanks for watching, and I'll see you soon.